let's look at an example of Young's double slit experiment. And this views light in terms of it being a wave. So let me just draw the typical scenario. So this is usually, okay, so this is, and it could be anything, like a piece of paper with two slits. So this is slit 1, slit 2, and if you shine light at the slit, you'll see two different I don't know what to call them, waves emanating from each slit. And eventually what will happen is when there's a screen located very far away from the slits, you will see this pattern happening right here. And this is important. This pattern is of equally distant pattern. So the distance from here to here is what we call y, and that's the same distance from here to here. So this central bright fringe, m equals 1, m equals 0, the next one, m equals 1, the next one, m equals 2, and so on. So here, m equals 1, m equals 2, and so on. So these are the bright fringes, and the space in between, those are dark fringes. So here you have m equals 1, as well as here, m equals 2, m equals 2. Okay, so this is a pattern that we see, and the distance between the slits, this distance here, is given the symbol d. The distance from the slits to the screen is L. Like we said, the height difference between the fringes is going to be a y. And of course, m is the number. It's the mth brightest fringe or mth darkest fringe. So let's look at this problem. We have a screen is separated from a double slit source by 1.2 meters. So that gives us L. L equals 1.2 meters. Okay. The distance between the two slits is 0.03 millimeters. So D equals 0.03 times 10 to the negative third meters. Okay. So a very small distance between the slits. The second order bright fringe, so m equals 2, is measured to be 4.5 centimeters from the center line. So from this central bright fringe, this distance here is 4.5 centimeters. So let's say that y from m equals 0 to 2 equals 4.5 times 10 to the negative 2 meters. Part A, determine the wavelength of light and the distance between adjacent bright fringes. So we're looking for wavelength, most likely going to be in nanometers. And we're also looking for the distance between adjacent bright fringes. So like I said earlier, that distance will always be the same. So we can go ahead and solve for part B. So for part B, we have the distance from m equals 0 to m equals 2 is 4.5 centimeters. So the distance between m equals 0 and m equals 1 is just half that. So y equals 2.25 centimeters. So that's the distance between m equals 0 and m equals 1, and as well as the distance between m equals 1 and m equals 2, as well as the distance between m equals 2 and m equals 3. Okay, so next let's solve for wavelength, so part A. So there are various equations that we could use, but let's use this, where y equals m lambda d m lambda L divided by d. Okay, so in the case if we're looking for wavelength, let's rearrange this. Divide by L to this. So we have wavelength equals the slit distance times the fringe height divided by whatever fringe we're considering times the distance between the slits in the screen. So 1.2. So if we're going to use m equals 2, we then have to use the fringe height of the second brightest fringe of m equals 2. So we have 0.03 times 10 to the negative third meters times y, which was 4.5 times 10 to the negative 2 meters, divided by m equals 2, just a number, times 1.2 meters of length. So you see that this will give us a unit of meters, which is good, that's what we want. So let's calculate it. 0.03 times 10 to the negative third times 4.5 times 10 to the negative second divided by 2 times 1.2. Okay, so let's see. Yep, I get 563 nanometers. So this is our wavelength of light. Alright, thank you guys for watching.